Okay, welcome back. This is now 11.2, so we're going to start worrying about orders of algorithms. So 11.2, we have big omega, um, big O, and big theta. My theta looks kind of like a cursive O notation. Okay, so what we're talking about is the number of times code executes some sort of idea, I guess. I don't know. One thing that's always was interesting to me is adding versus multiplication. So you could clearly see, at least I hope you could see, that the number of operations in doing something like adding two numbers, so we'll say 11 plus, um, I don't know, so 13. So that's 4. Okay, so that's pretty easy, right? But then compare that to 11 times 13. In this case, it's 3 times 3, and then I got to do another row of work. Oh my gosh, 1 times 1 is 1, 1 times 1. Am I done yet? No, got to do more. Okay, so I add the 3, and then 3 plus 1 is 4, and then 143. So what it seems like is if you were to count or produce some sort of measurement of the work involved, so you can count the number of levels, right? So in addition, there's 0, 1, 2 levels, and multiplication 0, 1, 2, 3, 4 levels for the same sort of operation, right? So you would say, okay, the multiplication must be harder. Okay, and we use that big O notation, big theta notation stuff to kind of put a measure on operations like these, like arithmetic operations. One cool thing about this is nobody knows if there does or does not exist an algorithm that will make multiplication kind of the same as addition. Okay, so maybe there's some clever way of multiplying numbers that nobody's ever thought of that will have the same kind of level as addition. Okay, and people work hard trying to do these kind of problems, especially, I guess, multiplication. And there's like somebody came out with fast Fourier multiplication or something weird a while ago. So it's a big research topic. At least it was for me. I'm old, so back in the day, people were really into this, trying to reduce the kind of order of multiplication. Okay. Okay, so there's that. You can, if you're interested, I can give you. Maybe I should do like another research assignment on that, but I don't know. I'm getting older. I'm not as ambitious. If you're interested, you can email me, and I will point you in the right direction. You could do the research. Okay, so anyways, let's get in there and take a look. So beginning with big omega of g of x, big O of g of x, and then big theta of g of x. I apologize for the homework in this section on WebAssign. I apologize on behalf of the math community. The homework, there's like 3 or 4 problems, and it, in my opinion, doesn't make you very much smarter for the wear. If it was my way, I would have you do written homework, but there it is. So you may want to do exercises in the book if you're interested in this topic. Okay. Anyways, what are these things? You could think of the big omega, which is the first one of g of x, is kind of a lower bound. Okay, so it's an at least sort of property. So f of x is going to be said to be big omega of g of x if and only if there exists a big capital A and a little a in the real numbers such that a times the absolute value of g of x is less than or equal to the absolute value of f of x eventually. So for some x greater than this a value. Okay. it's easier seen if I just draw you a graph of what they're talking about. And f of x represents like the number of operations you would have to do in an algorithm. Okay, so if you put in like, I don't know, 11 plus 13, f of x would output level 3, right? If I put in 11 times 13 into some other function, it would tell me that it has level 5 or something like that. Okay. All right, so we can use these graphs to represent the number of operations for maybe a given input. And so we're saying that there's this function g of x that is always going to be less than the number of operations on f of x eventually. Okay, so let this be the absolute value of g of x times a, and then x is on the x-axis, this x greater than a. Sorry, a is on the x-axis. Okay, so in the beginning, maybe f of x is bouncing up and down, maybe it goes below, but eventually it's going to go above g of x always. Okay, so this would be the absolute value of f of x. And we say basically the number of operations will always be above the number of operations given by g of x so long as you go out past a. Okay. All right. Secondly, then, f of x is big O of this function g of x. Basically just means it's bounded above. Okay. If and only if there exists a big B and a little b in the positive reals such that the absolute value of f of x is less than or equal to some big B times the absolute value of g of x eventually. So for x greater than some b value. Okay, so the picture in that case, again, we have this g of x function zipping out something like that, g of x. So this is b times g of x, excuse me. And what this is saying is that this function will always be above this f of x thing eventually. Okay, so maybe in the beginning and not so, but later on, yes, so. Okay, so here is b on the x-axis. Here is f of x, and who knows what it's doing in the beginning. It's sort of bouncing around. Maybe it thinks it's going to always be above it. And it goes up, and then it hits, and then, oh, it's never going to go above g of x. It's just going to kind of be below it all the time. Okay. Big theta then means it's bounded above and below. And usually what we're after is the big theta. So f of x is big theta of g of x if and only if there exists an a and a b, which are basically the a's and b's from above, and then a k value, which is the max of little a and little b usually in the real numbers, such that this function f of x, the absolute value of it, is bounded between some a value times the absolute value of g of x and some b value times the absolute value of g of x eventually for x greater than this k value we just introduced. Okie dokie. So in that case, it'll create kind of a tunnel where the f of x will exist. So here is maybe our g of x times, I don't know, the a of x, maybe I made it too big. Here's the other g of x. Okay, so the first one on the bottom one is a times the absolute value of g of x, and then the top one will be b times the absolute value of g of x, and then we have our f of x, which eventually is bounded by those two functions once we go past k. All right, so I maybe put it in a different color this time. So here is our f of x kind of bouncing around, doesn't know what it's doing, and then all of a sudden it's kind of trapped. I don't know, maybe it's going something weird like this, but it's always trapped. Okay, so here's the absolute value of f of x. Okay, so again, what we're after is kind of trapping these things with the big theta, and the book will spend a lot of time working with first just generalizing polynomials. Okay, so orders of polynomial functions. All the problems like in your homework where you're counting up number of executions, so maybe you had a for loop, so for I equals 1 to n, and then for j equals 1 to m, you know, how many executions would you have? You have some code here. All you have to do is multiply m times n, and that gives you well, maybe let's even make this 5, 1 to 5, okay? And then you go, your next j, and then your next n. So how many executions would there be here? There would be 5n executions, right? So you could say your function, or f of x would be kind of 5x, right, depending on the n value. And that's a polynomial. That's a polynomial that describes the number of executions this little code segment takes. Okay, so what we're trying to do in the beginning is just work with all of those kinds of forms, these polynomial forms for the representations of the number of executions of the code in an algorithm snippet. Okay, so orders of these polynomial functions. So our first example I want to show, and there's some inequality work we have to be able to stomach here as well, but what I'm trying to do right now is show for any x in the real numbers, if x is greater than 1, then 3x cubed plus 2x plus 7 is less than or equal to 12x cubed. Okay. So not exactly at the order stuff yet, but this is a kind of manipulation I need to be able to do. Okay, so it'll hinge on this fact. Note if r and s are in the rational numbers, or in this case we have r and s in the natural numbers, I guess, but let's just say rational numbers. And then if x is greater than 1 and r is less than s, then we can say x to the r is less than x to the s. Okay, so in general, a sub-example, so I'll say, oops, I don't want to say that, example sub s. If you have something like 5x, you can say that's less than or equal to 5x squared, so long as x is greater than 1. Okay, if x was less than 1, then when you square something like that, it actually will make it smaller. Okay, so we note then if x is greater than 1, we have 3x cubed plus 2x plus 7. It will be less than or equal to, well, 3x cubed plus 2x, and we can increase the power of that exponent x, right? 2x is less than or equal to 2x cubed, and that's from this notice right here that I'm putting in this box. Okay, and then likewise we could do that with 7. So we could say, okay, and that also means plus 7x cubed. Okay, and then that, what does that equal? Well, 3, 4, 5 plus 7 is 12x cubed. Okay, which is what we were trying to show. Okay, so that kind of operation is important. Also note then if x is greater than 1, we can slap in some absolute values on both sides of this. 3x cubed plus 2x plus 7, all of those terms are positive. So if you take the absolute value of it, it'll still be positive. And you could do that on both sides because both sides were originally positive. Okay, so on the other side, you'll have absolute value of 12x cubed, which will be equal to 12 times the absolute value of x cubed. Okay, so why do we need that? It's these definitions up here all have absolute values on them, so we kind of need to also worry about those issues. Okay, so an example of proving something is big theta. So we want to show that 2x to the fourth plus 3x cubed plus 5 is big theta of x to the fourth. Okay, so we note, whoops, I don't want to do big theta, I want to do big omega first. Or wait, I'm showing it's bounded. Okay, so yeah, my end goal is to show it's big theta. I'm sorry. Okay, so first we want to show that it's big O. Okay, so we're going to begin with the argument from above. So okay, so sorry. In order to show it's big O, we need to show. Maybe I should have done one at a time. We need to show it's big O of x squared and big omega of x. Sorry, x to the fourth and big omega of x to the fourth. Sorry. Okay, so anyways, we suppose that x is greater than 1, right? We note then 2x to the fourth plus 3x cubed plus 5 will be less than or equal to 2x to the fourth plus 3x to the fourth plus 5x to the fourth, which is equal to then 8, 9, 10 x to the fourth, right? And then I could apply absolute values on both sides and say this is 2x to the fourth plus 3x cubed plus 5 is less than or equal to 10 times the absolute value of x to the fourth. Okay, so well, now we're sort of fitting it into the definition for being bounded above, right? And then that's big O, right? So what that number 10 is the big B, and the x greater than 1. The 1 is the little b. Okay, so scrolling back down, letting big B equal 10 and little b equal 1 in the definition for big O of, in this case it'll be x to the fourth, we have that, yeah, this polynomial is O of x to the fourth. Okay, that 2x to the fourth plus 3x cubed plus 5 is big O of x to the fourth. Okay, so we got part of it done. We got this like first part here done. We need to show now that it's bounded below. Okay, and in order to show it's bounded below, so next I want to show it is bounded below. And in order to pull this off, we do a kind of another trick. All right, so I'm going to start with x to the fourth. In particular, I'm going to start with the first term of the polynomial, 2x to the fourth. Okay, so note, and again, I have to make an assumption with my x values. Before I said x greater than 1. Here I'm going to say x greater than 0 to pull it off. Okay, so the trick this time, start with the first term of the polynomial, 2x to the fourth, and then that will be less than or equal to anything you add in. Any x you add into that, it'll be less than that, because x is greater than 0. It'll be like adding another number into it, right? So 2x to the fourth is definitely less than or equal to 2x to the fourth plus pretty much anything. So why not add in the other parts of the polynomial, 3x cubed plus 5. Then, because x is greater than 0, both sides are greater than 0, so you could take the absolute value of both sides. Okay, and you'll end up with 2 times the absolute value of x to the fourth, which is less than or equal to the absolute value of 2x to the fourth plus 3x cubed plus 5. And now what we've done is fulfilled the definition for big omega, right? So we've shown that it's kind of bounded below, where our a value, big A this time, up here to the right, this big A is the 2, the leading coefficient of the polynomial, and the little a this time is 0. Okay, so what we're going to say then is letting big A equal 2 and little a equal 0, we have the definition, or we have fulfilled the definition for the polynomial being big O of x to the fourth. So for 2x to the fourth plus 3x cubed plus 5 is big omega of x to the fourth. Okay. So once you've shown that something is big O and big omega of the same thing, okay, so because the polynomial is big O of x to the fourth and big omega of x to the fourth, we can conclude it is big theta of x to the fourth. Okay. In particular, if you don't believe me, you just let, in this case, a equal 2, b equal 10, and then k is equal to the max of a, which is, I think we said it was 0, and then little b, which is 1. Okay, which in this case will give you 1 for your k value, which will lead to the fulfillment of the definition for big theta. Okay. From this point on, the book will carry on with this exploration, and it'll convince you that even if we have, so from this point on, the book notes, even if you have a polynomial that doesn't have all positive terms, for example, let's say 3x to the fifth minus 2x to the fourth plus 3. Even though it has a negative sign in there, you can adapt the arguments to make sense of this thing, and it'll end up being big theta of x to the fifth. Okay, I'm not going to go through that. It's a little complicated, and I think we can probably stomach the end conclusion. So ultimately, we have the following for polynomial orders. So given a polynomial a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a sub 1x plus a sub 0, first off, this thing is big O of x to the s for any s that is greater than or equal to n. Okay, so that's the bounded aboveness. So for example, 3x to the 5th is big O of x to the 20th. It's big O of x to the 30th. It's big O of x to the 6th. It's big O of x to the 5th. Okay. Secondly, then, it's bounded below by any polynomial term x to the, let's say, r, whenever r is less than or equal to n. So 3x to the 5th minus 2x to the 4th there at the top of the screen is big omega of x. It's big omega of x squared. It's big omega of x cubed. It's big omega of x to the 5th. Okay. Thirdly, then, this polynomial is big theta of x to the n. Okay, you could do the same thing with rational functions. I think we'll just leave it at this, though. And there's a bunch of theorems in the book. We're not going to harp too much on it. I think we'll just, for our work, knowing the polynomial orders, hopefully will get us through it. And if we need anything extra, I'll throw it in as we go through Chapter 11. But I think this will do it for us. And we'll see you next time. Okay, thanks for watching.